Today, we want to talk just briefly about hyperbolic trig functions, the hyperbolic cosine, and the hyperbolic sine. So these are functions that come up a lot in engineering applications, or so I'm told, not being an engineer, but as a math teacher, I have to be familiar with all aspects of all science everywhere for reasons, I guess. So my engineering colleagues tell me that, yeah, hyperbolic cosine, hyperbolic sine, that's a big deal. Here's how we define the hyperbolic cosine and the hyperbolic sine. They're just combinations of e to the x and e to the minus x. From a calculus standpoint, we want to know the derivatives of each of these functions, and the derivative of hyperbolic cosine is hyperbolic sine. The derivative of hyperbolic sine is hyperbolic cosine. This is easy to see because the way that we define hyperbolic cosine is e to the x plus e to the minus x all over 2. So when we take the derivative of e to the x is e to the x. That's that first term. The derivative of e to the minus x is minus e to the minus x. So the derivative of hyperbolic cosine is hyperbolic sine. Going back the other direction, the derivative of hyperbolic sine is hyperbolic cosine. The derivative of e to the x is e to the x. And the derivative of minus e to the minus x is minus a negative e to the minus x. So the negatives cancel and we get plus e to the minus x. So from a doing stuff in calculus standpoint, the derivative of hyperbolic cosine is hyperbolic sine. The derivative of hyperbolic sine is hyperbolic cosine. Fun fact about hyperbolic cosine is that the shape of a chain or a rope or some other kind of string hanging under its own weight will be the shape of a hyperbolic cosine. This shape is also known as a catenary. So when you're out and you see power lines suspended between two poles or telephone lines between two poles, there's a little bit of bend down that you can see in the wire, and that shape will be a hyperbolic cosine because the only thing that's on that wire is its own weight. I suppose if birds land on it, then there might be some additional weight on the wire. But I don't think the weight of a couple of birds is going to change the shape that much. All right. One of the problems that we had in the homework, which I think caused a little bit of confusion, was confusing because we did not need to know anything about derivatives. So we were just given that a cable between two towers hangs in the shape of a curve. It says of a suspension bridge. I'm hoping that the bridge is not being suspended from it yet because that would change the shape, but that's all right. So homework 3, section 8, problem 1. We had the shape of a cable between two towers of a suspension bridge was given by y is t over w times a hyperbolic cosine of wx over t. In this case, T is the tension in the cable at its lowest point. And W is the, let's see, the weight of the cable per unit length. So it's the length, the weight, length, weight, density of the cable. Weight of the cable per unit length. At this point, we might be thinking, I'm not sure how to measure tension in a cable. What kind of units are we using? Then we read on further and we realize we don't need to know. So the curve is called a catenary, like we said. The cable stretches between the points x equals negative t over w and x equals t over w. So we've got this cable hanging down, and it's hanging between the points x equals negative t over w and x equals t over w. Oops. There we go. And we also told that the sag of the cable is defined as the difference between the height of the cable at its highest and lowest points. So the sag of the cable is the difference between the highest and lowest points. And we're asked to show that the sag of the cable can be expressed as a multiple of t over w. So our job is to show that sag is a multiple of t over w. So this is going to require us to recognize some things about this particular function. One thing that we can note about the function hyperbolic cosine is that hyperbolic cosine is an even function. Notice that if I plug in opposite values, I'll get the same thing. F of negative x is equal to f of x. Note. Hyperbolic cosine is an even function. F of negative x is equal to f of x. We could demonstrate this by looking at e to the negative x. So this is going to, hyperbolic cosine of negative x will be e to the negative x plus e to the negative x over 2. And notice that the two negatives in this second term cancel out. We end up back where we started. Hyperbolic cosine is an even function. That means that the hyperbolic cosine is symmetric, has vertical symmetry. It's symmetric about a vertical line through the middle. It has a middle at 0, and it's symmetric about that vertical line. So when x is equal to 0, we have the graph is symmetric about the vertical line x equals 0. What that tells us is that the value of the function at t over w is the same as the value of the function at negative t over w, which is good because that's the way I drew it. So all we need to know is the value of the function at t over w and the value of the function at negative t or at 0. the difference between those two will be the sag. So the sag that we're looking for is the difference between the value of the function at t over w and the value of the function at its lowest point when x is 0. And we're going to find the, oops, that's not the function. We're not just plugging right into the hyperbolic cosine. So it'll be the difference between our original function at t over w and our function evaluated at 0. So we just take t over w and plug it into our function for y, and then plug 0 into our function for y, and subtract the two, and see if we get a multiple of t over w. So if we plug in t over w, the function is t over w times the hyperbolic cosine of w over t times t over w. And then we subtract t over w times a hyperbolic cosine of w over t times 0. That's the difference between the highest point and the lowest point. The highest point will happen at t over w, which is the same as the height at negative t over w. And the lowest point will happen at 0, which is in between. So plug these values, t over w and 0, into the hyperbolic cosine, and then subtract and see if you get a constant. Any questions? That was the problem that was on the homework. It didn't involve anything about derivatives. It was more about stuff that we know about functions in general. And it was also taking stuff that was defined for us in the problem. So we don't have to know anything about catenaries. We don't have to know anything about sag in cables or tension or weight. We have been told that this is the shape of the chain, or the wire, or the cable. And we know that it should be this vague U shape. Then we had to bring in some other stuff that we know about functions so that we can conclude that the height at t over w and negative t over w will be the same, and that the lowest point will be halfway between those two at 0. Any questions?
Yes, Professor Leach. On the right, you have the note. It said cos x is an even function, and then f negative x equal fx. My question is right here. Cos negative x is equal e negative x. So that's it, the formula. How did you come out with, on the right, e to the x plus e power of negative x?
So
how you come up with the right e, the power
e to the negative x?
Yes, I got that part.
That becomes e to the x.
Oh.
And e to the negative x is e to the negative x.
Oh, you kind of like switch the order. Okay.
Yeah, it's addition, so I just wanted to make it look like
okay. One more thing. On the left, on the bottom, you said sag equal. Where you get this formula, y? So this is the function, isn't it? Y? T over
this was defined for us. The problem states that the sag of the cable is defined as the difference between, so the sag is the difference between the height of the cable at its highest and lowest points. So here's where we have the highest point. Oops. And here's where it will be at the lowest point. So we were given that sag is the difference between the height of the cable at its highest and lowest points. So I just had to translate that into the value, the function at its highest point and the function at its lowest point.
And one step below, this is the function, isn't it? T over W cos, W over T, multiply T over W.
Yeah, that's just taking T over W
You
and
plug
plugging
it
it
in.
into the function Y. So T over W into this
X.
function.
Wow, I see it. Okay.
We're saying X equals T over W.
And then the last step, negative TW, how do you come out with that?
So this minus here
Oh,
is this minus here.
okay.
So this first piece right here is Y of T over W, and this second term is Y at 0.
Okay. Well, I will figure it out later, but it's good enough.
Everybody gets to tell Minecraft, Steve.
So this term here.
Would you let me
Now I'm
have
just including what
intellect? My pocket.
I'm just writing the formula, the function Y with how we actually calculate Y. This first term here is that first term.
And what would be the answer for this question? The answer?
Just plug in 0 into this function in the hyperbolic cosine, which is the difference, or the e to the x plus e to the minus x over 2.
Okay.
Just plug those values in and then subtract, and you should get a multiple of TW. So whatever you come up with, you should get some constant times T over W.
Well, I'm gonna work on that. If I have a question, I'll get back. Thanks, Professor Lich. Thanks.
All right. So there's another question. This question is going back a section. So there was a question on, I got an email question about hyperbolic, from the hyperbolic functions. So we should talk about the hyperbolic functions. We didn't get to the interesting stuff about hyperbolic functions. Here's a brief. If we have a unit circle, x squared plus y squared equals 1, then the coordinate and we have a circle, a unit circle. We know that the coordinates of the points are going to be cosine theta, sine theta, where theta is the positive angle from the positive x-axis. If we trade our unit circle for a unit hyperbola, by trading our positive y squared for a negative y squared, so our x squared minus y squared equals 1, we end up with a unit hyperbola. We could do the same thing. We could measure an angle from the positive x-axis. But we won't have cosine and sine, we'll have hyperbolic cosine and hyperbolic sine. So, trig facts. There was another question on chapter 3, section 7, Problem number 6. This is back in the implicit differentiation. So we've got this nice, cool, messy function going on. We've got e to the cosine of y equals x to the 4th arctangent y. And we want to find dy dx. So remember our process. We're just going to take the derivative with respect to x all the way through. And then we're going to solve for dy dx. The thing that we have to remember is that we're going to, when we take the derivative with respect to x, we find the derivative with respect to y and multiply by the derivative of y with respect to x. So we're going to find the derivative. We have to find the derivative with respect to y. And then the chain rule says we have to multiply by the derivative of y with respect to x. So we're going to have to remember to use the chain rule. All right, so let's take, and we're also have to remember all our other rules for taking derivatives. So good training exercise. Let's look at the left. We want to take the derivative with respect to x of e to the cosine of y. So the derivative of e to the something is e to the thing times the derivative of the thing. So now we need to multiply by the derivative of cosine of y, which is negative sine y. But when we go from cosine y to negative sine y, that's the derivative with respect to y. Now we have to multiply by dy dx. Because of the chain rule. So we're using two chain rules here. So the derivative of e to the cosine y with respect to x is e to the cosine y times the derivative of cosine y, which is negative sine y, times the derivative of y with respect to x, which is just dy dx. Next up, on the other side, I've got x to the 4th times the arctangent of y. So I have two functions being multiplied together. I would take the x, I would plug it into x to the 4th. I would hold that while I take y, plug it into arctangent, then multiply the two results. So this says we're going to need a product rule. So on the right side, we're going to take the derivative of the first times the second plus the first times the derivative of the second. And the derivative of arctangent is 1 over 1 plus y squared. But implicit differentiation but the chain rule says we have to multiply by the derivative of y with respect to x. 1 over 1 plus y squared is the derivative of arctangent y with respect to y. So the chain rule says multiply by dy dx. We should algebra this up a little bit. So this term I have a minus. I have to make sure I had to make sure to put parentheses in here because this term is now negative. So I'm going to rewrite this as minus. Let's see. I'm going to write e to the cosine y times sine y. Times dy dx. This can stay as it is, 4x to the 3rd arctangent of y. I'm going to clean this up by putting the x to the 4th on top. But then I have a dy dx. So now we've gone through and done the calculus part. We've taken the derivative with respect to x of both sides. Next is to do the solve for dy dx part. So we got to get all the dy dx terms on one side. So let's see, here's a dy dx term. This term is not dy dx, but this term over here on this side is dy dx. So I've got these two dy dx terms. I want to get them on one side of the equation. And I'm going to get my non-dy dx term on the other side of the equation. So I'm going to put I can just subtract x to the fourth over 1 plus y squared dy dx from both sides of the equation. So I'll have a minus e to the cosine y times the sine of y times dy dx. I'll subtract the x to the fourth over 1 plus y squared times dy dx. So all my dy dx terms are on one side of the equation. On the other side of the equation is just 4x cubed times arctangent y. We're solving for dy dx. So the next thing to do would be to factor out the dy dx on the left. And now I've got all this stuff times dy dx is equal to 4x cubed arctangent y. So I just need to divide to solve for dy dx. So dy dx is on the top, we'll have this 4x cubed arctangent of y. On the bottom, we'll have a minus e to the cosine y times the sine of y minus x to the fourth over 1 plus y squared. Any questions? This all seems very messy, but we have to look at what we're solving. We're trying to solve for dy dx. And here I've just got a bunch of stuff times dy, stuff that's not multiplied by dy dx, sorry, bunch of stuff times dy dx, some stuff that's not multiplied by dy dx, and then some stuff that is multiplied by dy dx. So this equation is stuff times the thing we're looking for, some stuff, and then some more stuff times the thing that we're looking for. This equation might as well be 5 is equal to 7 plus, or 5x equals 7 plus 3x. Something times the thing that we're looking for equals non-x term plus 3 times the thing that we're looking for. And we did the same thing. I subtracted the 3x from both sides to get all the x terms on one side. I factored out the x and then divided by the coefficient of x. Algebraically, it was that same structure. It's just that instead of x, we had dy dx, that's the thing that we're looking for. And instead of 5, we had this minus e to the cosine y times sine y. Our coefficients were just messy, that's all. Any questions? Rad.
Can we do a little bit of review of the chain rule?
In what way? What is it about the chain rule? Specifically about this problem, because that's what raised the question.
Okay. I guess it's not so specific then. I'll just go back and watch your videos.
So the big idea is that the chain rule, when we take a derivative, let's start with the base idea. So we know that the derivative with respect to x of, say, x to the n is equal to nx to the n minus 1. And so we know how to do this, right? This is the first thing that we started working on. The derivative with respect to x of 5x to the 7th will be 35x to the 6th. Because there's so many words that we could pile on to this, we just say the derivative of 5x to the 7th is 35x to the 6th. And so the words that go along with this, we usually simplify. We leave off some important information. We're leaving off some important information. The derivative with respect to x, so we just say the derivative of 5x to the 7th when we read that set of symbols. Is because we're a little bit spoiled. We're in single variable calculus. We only ever have one variable to deal with. Everything's just a function of one variable. Even when it's not a function, we're just using one independent variable. But we leave off some information when we just say the derivative of 5x to the 7th. This is the derivative with respect to x of 5x to the 7th. It's that derivative of 5x to the 7th. So when we see an expression like 5y to the 7th, or let's say 5 times the cosine of x to the 7th, we still want to see the 35x to the 6th in this expression. So the first thing that we write is 35 cosine of x to the 6th. This is the derivative with respect to cosine, but we want the derivative with respect to x. This is the derivative with respect to cosine, so we have to multiply by the derivative of the cosine with respect to x. So when we see 5 something to the 7th and the derivative is 35 that thing to the 6th, then we have to multiply by the derivative of the inside. So saith the chain rule. So this first piece the first factor is the derivative with respect to the cosine. The second factor is the derivative of the cosine with respect to x. That's the idea behind the chain rule. We have to think about what is the variable in play when we apply our derivative rules. All that we're doing now is, instead of having something explicit like cosine of x, we're saying if we have 5 times y to the 7th power, when we write 35y to the 6th, when we write 35y to the 6th, this is the derivative with respect to y. But we want the derivative with respect to x. So we're not done. We've just written down the derivative with respect to y. That means we have to use the chain rule and multiply by the derivative of y with respect to x. That's what the chain rule says to do. It's different if I asked for example, what's the derivative with respect to y of 5y to the 7th? We would just be able to get away with writing 35y to the 6th because we're using y as the variable. That's the derivative with respect to y. I applied the rule to the variable y. So the derivative with respect to y of 5y to the 7th is 35y to the 6th. Done. But if I want the derivative with respect to x of 5y to the 7th, I need to write 35y to the 6th. That's the derivative with respect to y. Then I have to use the chain rule and multiply by the derivative of y with respect to x. That's what the chain rule wants us to do. This is how we think about the chain rule so that we can apply the chain rule when it shows up. It's important to always think about the chain rule and not just kind of go on autopilot. So it's handy to say derivative of the outside leaving the inside alone, then multiply by the derivative of the inside. A lot of times that's useful wording to get us to the derivative, to get us to apply the chain rule correctly. But in addition to that, we need to understand what the chain rule is telling us. We need to understand what the symbols mean when we write d over dy times dy dx. Any other questions?
Yes, Professor Rich. Could you go back to the problem just now, 3.7, number 6 on the homework? Yes, this one I did it with the help from the STEM Center. I got it right. My question is right here. Where you put the square with the yellow on top of it, we have e cos y multiply negative sine y dy dx. And then on the bottom, okay, I'm sorry. The first one, the function on the top, very on the top, e, power cosine y. So you put it out, it's the same. And then you take the negative from the cos y. So it becomes negative sine. Could the y go away? No, right?
No. So if you just write sine by itself, that doesn't mean anything. It's the sine, it's not the sine, it's sine y.
Yeah, I thought it was, in my thought, as long as we have negative sine, dy dx, then we're okay, but we know.
No, sine means nothing by itself.
I got it.
It's got to be sine of something.
Whatever the x there, we put the x. If the y, whatever there, we need to put it the way it is.
Yeah.
Okay, got it. Thank you, Professor Leach.
That's the derivative of cosine with respect to y. Then we multiply by the derivative of y with respect to x using the chain rule. We had two chain rules in that term.
Right.
Any other questions? All right, remember, this only seems like it's a lot to remember because it's a lot to remember. You have to remember all of it all the time in all of the details. In addition, most of the time, you're being expected to remember things that you never knew in the first place. So we're taking your algebra and pushing your algebra much further than it's been pushed in the past. So not only do you have to remember all this new stuff and all of those details, you have to remember stuff that you never knew in the first place. You have to be able to do things that were never called upon to do. And you have to start seeing those things as just being the same as old things. So in addition to learning new stuff, you have to see some old stuff in new contexts and identify it as old stuff in new contexts. I think this is one of the things that we don't do enough when we're teaching people math. We don't just say, this is old stuff in a new context. In fact, I know for a fact this happens because I've read an algebra book, and I'm still looking for an algebra book whose first sentence says, algebra is just arithmetic. All those things that you know how to do in arithmetic are things that we're going to do in algebra. Algebra is just arithmetic. I've never seen a book that came out and said that. So I'm going to say it on this video. Inspire some math author to write a book, or it's an algebra book in the context of arithmetic, and then do a bunch of TED Talks explaining how it's so simple. Then a bunch of schools adopting this book, but the teachers aren't prepared to use it. So only the initial pilot will have success. And then after that, people saying, no, let's just go back to some other way, because they weren't really prepared. It works just like diets is what I'm saying. The reason that any diet that you start trying in the beginning will work because you're paying attention to what you're eating and what you're doing during the day. Once it starts becoming routine, you stop paying attention, you start going back to your old habits, and then you declare the diet to be unsuccessful. You know what I mean? Same thing happens with like math ideas. All right. That's going to do it for today. Let's see, today is Tuesday. That's going to do it for today. We'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.